All right, welcome to our next video in the circles unit. And today we'll be exploring the properties of tangents. Let's do some vocab first. Now this is not in your notes, so make sure we write this in somewhere. All 5 of these are important. So go ahead and pause the video and let's write down all the vocab. All right, so our first vocab word is radius. We've dealt with radius and diameter. These are probably 2 that we should know previously. Radius is a line segment with one endpoint at the center of the circle and one endpoint on the circle. So this is an example of what a radius would look like. Next is a chord. A chord is a line segment with both of its endpoints on the circle. So endpoint 1, endpoint 2. Connect those endpoints. That's an example of what a chord is. All right, so a diameter is gonna be a chord, meaning it has endpoints on the circle, but it's going to be a chord that passes through the center of the circle. And as we know, the relationship of radius and diameter, radius is half the diameter, or diameter is 2 times the radius. All right, so those first 3 line segments all represent line segments. They're all going to be segments, and they're all located inside of the circle. None of them ever come outside the circle. They're all contained inside the circle. Our last 2, secant and tangent, are 2 lines that will go outside the circle. First of all, we have a secant, and a secant, it can be a line segment, or it can be a ray. It has exactly 2 points of intersection on the circle. And then we have a tangent line. Now this is different from tangent that we did with trigonometry, different type of tangent. Tangent is going to be, again, a line segment array with exactly 1 point of intersection. So it's going to come by the circle, and it's just going to barely touch the circle at 1 point. And that point where it touches is going to be called a point of tangency. And like I said, that's going to be the point at which the tangent line touches the actual circle. All right, so let's identify, based on this diagram, what these are going to be. So we want to know if it's going to be a radius, a chord, a diameter, a secant, or a tangent. So start with the segment BC. Segment BC has an endpoint B and C. Okay, it's entirely located within. All right, so segment BC has endpoints at B and C. And one of those endpoints is the center of the circle, the other one being the actual circle itself. This is the definition of a radius. So BC is going to be a radius. Next, we're going to look at line EA. So line EA, here's point E, here's point A. This is line EA. Now we notice this goes outside the circle, so it's not going to be a chord, it's not going to be a radius or a diameter. It has to be either a secant or a tangent. So we're looking for points of intersection. It intersects a circle right here at F, and then again at A, so 2 points of intersection makes this a secant. And last, we have ray DE. So ray DE starts right here and goes to the left through points B and D. Again, this is outside the circle, so it's either going to be a secant or a tangent, so we're looking for points of intersection. It has 1 point of intersection for the circle, which is point B, so this is going to be a tangent. In example 2, we're going to explore what we call common tangents. So I have 2 circles. I want to know how many lines can I draw that will be tangent to both circles. Now the first example that we have here, these circles are actually tangent to each other, meaning they have 1 point of intersection right here. So we can draw one line that goes on the right side of the circles like this. It's tangent right here and tangent right there, so there's 1 common tangent. But you can draw a second line, do the same thing on the other side, 1 tangent point, 2 tangent points. Okay, so tangent both circles. And then we can also draw a line right down the middle that's going to go through that point of tangency between the 2 circles. So with circles like this that are tangent to each other, we have 3 common tangents. Now for B, again, we can go on the sides. There's 1 common tangent. there's a second common tangent. So if I want to try to put another common tangent here, if I try to do this tangent to this circle, the small circle, okay, it's going to be secant to the big circle. If I try to go tangent to the big circle, it's going to be secant to the small circle. So this is really all we can do with the tangents here. I can only have two. So when I have two circles that intersect like these ones, I only have two common tangents. Now the last one, these two circles are tangent just like the first ones. However, the tangent circle is inside of the bigger circle. So we really can't put any common tangents on here because we'll get secant segments here. So what I'm going to look for is this point of tangency right there, and really that's the only line that I can draw. That's not going to go to have two intersection points in other circles. So when I have secant circles, or with the smaller circles inside the big circle, we're only going to have one common tangent for this one. All right, this theorem talks about if I have a tangent line, a line is tangent to a circle, if and only if the line is perpendicular to the radius. So in the diagram here, OP is a radius, line M is a tangent line, okay, and the radius and the tangent line are going to be perpendicular to each other. So we have a right angle, like in example 3 here, what we can do is we can form right triangles and use properties of right triangles to find missing sides. So what we're doing in example 3 exactly is verifying, is ST tangent to circle R? So if ST is tangent, that means this angle right here will be a right angle. So what I want to know, is triangle RST a right triangle? So we can use Pythagorean theorem to verify this. So the two legs would be, RS would be one leg, that would be 10 squared, plus my other leg, which would be 24, that's ST. And I want to know, does that equal RT, which is 26? So 26 is the entire length of this whole side right here. Goes from end to end right there. So let's go ahead and simplify. 10 squared is 100, 24 squared is 576, and 26 squared is 676. 100 and 576 makes 676, which is equal to 676. So yes, ST is tangent, okay, because this triangle is a right triangle. All right, moving on to example 4. So in the diagram, B is a point of tangency. So we're given that AB is tangent to circle C. We want to find the missing radius. We don't know what the radius of this circle is. So again, because we have a point of tangency, we can say that AB is perpendicular to BC, making triangle ABC a right triangle. So it's going to be leg squared. So the first leg would be BC, that would be R. We don't know what the radius is, squared. Plus my second leg, which would be 77 squared, and that's going to equal my hypotenuse. Now my hypotenuse is going to be this entire length of AC. Okay, the radius goes from C to the end of the circle right here, and then A from right there, that's going to be 49. So these two things together make the hypotenuse, so I'm going to add them together. So R plus 49 squared is going to be my hypotenuse. So we can go ahead and simplify. We'll go ahead and 77 squared, 5,929. And with this, I'm going to kind of take this off to the side here and remind ourselves, when I square a binomial, R plus 49 squared is the same thing as R plus 49 times R plus 49, and I need to distribute. So R times R is going to be R squared. R times 49 is going to be 49R. 49 times R is 49R again. And then 49 times 49 is 2,401. These are going to be like terms. So go ahead and combine them. I'm going to get R squared plus 98R plus 2,401. Now at this point we need to get we want to get r by itself. So we have r squareds on both sides, and I'm going to go ahead and subtract r squared from here, subtract r squared from the right as well, and what's going to happen is these are going to cancel out. And I'm going to be left with 5,929 is equal to 98r plus 2,401. The numbers are a little big, but it's just a two-step equation that we are perfectly capable of solving. So let's go ahead and subtract 2,401 from both sides. 5,209 minus 2,401 is going to be 3,528. That's going to be equal to 98r. Last but not least, divide both sides by 98. That we're going to talk about here is going to be intersection of tangent segments outside the circle. So what we have here is we got QR and QS, and that are both outside the circle. Sorry, so Q's outside the circle, tangent segments, and tangent segments that form a common external point are going to be congruent to each other. So in this case, you're going to have QR congruent to QS. So in this particular case, we can just say, you know, with these ones right here, QS is 3x plus 5. And that's going to be equal to QR, which is 32. And again, two-step equation, subtract 5 from both sides. 3x equals 27. Divide by 3, and x is equal to 9. So when you have two tangent segments with a common external point, we just set them equal to each other to solve. All right, now it's time to try the problems on your own. So give them a shot. Make sure you guys are writing down questions if you have them, and have a good day.